Can see your whole desktop.
Really?
Yep.
Let's see, share screen. Oh yeah. There we go. How's that?
That. That's good.
That's good. Who do we got here? We got Richard Grace, Jeff Wise, Andrew Corkill, Martin Eastburn. Excellent.
It's time for the Scott and Jerry show.
The Scott and Jerry show. That's right.
You should. I remember when I was
Scott and Jerry, written by Scott and Jerry, performed by Scott and Jerry, directed by Scott and Jerry,
a kid.
lighting by Scott and Jerry.
One of my best friends when I was like 8 years old, his name was Tom, and we were always Tom and Jerry, Tom and Jerry.
Tom and Jerry, perfect.
I noticed this doesn't have the countdown timer.
Yeah, it does.
It does?
Yeah, it's in
Where?
there.
Is it hidden?
It's hidden.
Oh, there's Jenny's on. I see. Hello.
Yeah, Jenny Bedell Shelley. Yep, Jenny, it's Photometry Today. Well, hello everybody. This is Scott Roberts and Jerry Hubbell, the Scott and Jerry Show.
Yep.
And today is going to be we're going to learn more about photometry, and this is something that Jerry and his team at the MSRO are deeply involved with, and you know, it's something that you can get into as well. I mean, all of us have heard about the magnitude ranking of stars and how we use magnitude estimates and measurements to, you know, apply that towards almost everything that we can observe or detect with our telescopes. So,
Right.
yeah. And so, Jerry, how did the magnitude in the system get started? And you know, who is the one who's credited with developing photometry?
So just as last week we were talking about astrometry, and Hipparchus was involved with that, creating the first star charts. He's also credited with creating the magnitude system. And I'll share my screen. Let me get something focused here, and then I'll share my screen and we can talk about that. I guess, do you want to do some introduction first to find out who's on the show watching before we get started on my presentation?
Yeah, so we have Richard Grace, who signed on first, and then Jeff Wise is on, Andrew Corkill, Martin Eastburn. He says, here we are, howdy from East Texas. It's hot here in Arkansas today. It's clear and very hot.
Mm-hmm.
Andrew Corkill says hello. Harold Locke says howdy. And Mike Wiesner says it's time for the Scott and Jerry show. That's what we said. That's right. Jenny Bedell Shelley says hello. I like her middle name, Bedell. I think it's a classic middle name. Let's see. Cameron Gillis is on, of course. And Mirko Mayer, hello from California. So hello, how you doing, Mirko? We've got, that's her maiden name, Bedell. Okay, very nice. Cameron Gillis says, I want to learn how to do photometry with non-stellar DSOs. Okay. Chris Larson's on, and I think that kind of, that's who we have.
Yeah, so there's when you're, well, we can talk about this. That's not part of my presentation, but that's an interesting question that Cameron brings up in terms of measuring the magnitude of extended objects versus point sources. So there's some things to think about there that we'll get into a little bit. I think I can remember to talk about it.
Yeah.
I'm writing it down so I don't forget it.
Don't forget.
I'm sure Cameron can remind me. All right, so let me share my screen. So this week and last week too, I'm pulling this from a presentation I created probably 6 or 8 years ago that I gave to our astronomy club. Do you see that?
Yes.
Guess I could make it a little bit bigger by stretching this a little different.
Now, I've seen Hipparcos's name spelled C-H-U-S.
Yes.
O-S.
Mm-hmm.
I guess
so. U.S. I think U.S. is like the Latin spelling. O-S is the Greek spelling. I think.
Okay.
I think that's the difference. I may be wrong, but if somebody wants to look at that, but in my book I actually spell his name with the O-S also. So I'm not sure where I picked that up, but also we talked about the satellite that went up that was named Hipparcos.
Yes.
And it's spelled out but left out the H.
Right.
So I think we can find out that maybe I think it's the Greek spelling is with the O. Anyway, he was a Greek astronomer, and he created a catalog of stellar positions of at least 800. He also created the first magnitude system, which ranked the stars from magnitude 1 to 6. with 1 being the brightest and 6 being the dimmest that you could see with your naked eye. Since that's all he had at the time, he didn't have lenses or anything to magnify or to gather more light and see dimmer stars. That's all he could go with. But it was an interesting coincidence because magnitudes 1 through 6 is 5 levels of magnitude, and it just so happens that the brightness range have to be from 1 to 100 for 5 magnitude for a 5 magnitude range, which is pretty interesting. And the fact that your eye responds to light in an exponential way or logarithmic scale makes it that much more interesting in terms of that. So, but it's not an exact correlation, I think. And then so English astronomer Norman Pogson in 1856 basically created the standard to define that brightness range as fixed. And then I'm not sure how he picked the stars. I think is it Vega? I can't remember now. Or Sirius.
Sirius must have been
Sirius is the brightest star.
Yeah.
But that's a magnitude 0 star. So that's actually brighter than a magnitude 1 star. So I'm not sure exactly how they defined the 0 point and the the magnitude 1 exactly.
Maybe it was a revision.
Yeah.
Possibly it was a revision, because I imagine Hipparchus probably did, magnitude 1 is the brightest.
Yeah, that's right. So Sirius for him would have been magnitude 1.
Yeah. Yeah. And then maybe with this logarithmic scale, this refinement, they go, okay, well, let's make Sirius 0,
Right, right, exactly. So this is the equation for magnitude. And that x value is negative since the scale's inverted. The brighter objects are lower values. But it happens to be that when you figure out that equation, x is equal to minus 2.5. So it's easy to remember if you remember this equation. The constant that you remember is minus 2.5. And it's always a relative brightness ratio. So you have to pick what you're comparing it to. There's no there's an absolute magnitude scale that's really based on energy measurement, okay? But you have to know a lot of details about the star to understand, okay, what is the absolute magnitude of this star? It's at a specific distance. It's at a specific energy that you're gathering with the instrument. So the scientists have, over the last, I imagine, 50 to 75 years ago, have determined how to calculate absolute brightness for stars. But in the day-to-day use of magnitude, it's a relative brightness measurement. To calculate a magnitude precisely, it's a relationship between two stars, not just one, or relative brightness. And we use standard stars to do this with, right? So we know the scientists have measured a lot of stars in terms of their specific brightness and their magnitude, and they say, okay, we're nailing this down to this magnitude is 3.72 for this star in the visual band. Okay, that's so you qualify it that way. So now you've got a reference star that you can compare an object to. That's okay. I know that this is 3.52 magnitude in the V band. What is this star? And you can measure it, the brightness of those two stars, and then calculate the ratio of the brightness, and then you can have a good estimate, a pretty precise estimate of what the brightness is of that new star, if it doesn't happen to be in a catalog. Or a better example of that is if you're measuring a solar system object like an asteroid, and you don't know what the current brightness is. So now you use a reference star where you know what the brightness is, and you compare it with what the measurement is for the asteroid, and that's really the way you use it today. So to get back, Photometry is the relative measurement of the flux or intensity of an astronomical object's electromagnetic radiation. They're done at various wavelength passbands using filters. There's a standard. There's several standards for photometric measurements, and it's called a photometric measurement. And the one that's most popular is the Johnson-Cousins system. And so it's a UBVRI system. And Johnson's created the UBV portion, which is ultraviolet, blue, and visual, and Cousins created the red and infrared portion of it. So that's what those mean. And this kind of gives you an idea of the passband for those different wavelengths for the filters. So basically, when you state a magnitude, when you measure brightness of a star, you basically want to state what passband is it in? Is it in the V band, or is it in the blue, or is it in the ultraviolet? That type of thing. Now, this was created. Original measurements of star brightness, relative measurements, were done visually. Okay. And so your eye's response to light is what the V-band filter is all about. That's this green one right here. Can you see that? So this is a way to match historical measurements with the visual measurements of brightness to stars with today's instruments that we have today with this filter. You can correlate the two, and they're pretty close to each other. That's how that filter was designed, and then everything else was added after that. Let's see. So the AAVSO is basically founded on the idea of doing visual measurements of variable stars, and from that information create light curves. So I'm going to go to the AAVSO website for a minute, and you can list it in the link if you want, Scott.
Okay.
And it's aavso.org. They just recently updated their site. Looks pretty good.
Okay.
It's more modern looking. Can you see that? Oh, my dogs are barking because the phone's ringing.
Variable stars always get your dogs going.
Yeah. So there's a lot of tools on the AAVSO, but if you're interested in photometry and using it for something practical and scientific, the AAVSO is where you want to go and learn all about it. So one of the things that they have plot a star curve. So let's see, what's a good name for a star that we can think?
Chris Larson said variable stars make him bark.
See if I can know how to spell Betelgeuse. Is that how you spell it?
That's right.
Oh, is that right? I don't know if that's right.
BETEL
GEUSE. Let me see.
Did I spell that right?
I don't know. Let's see if it finds it.
BETEL.
Oh, there we go.
USE.
All right. So
look at that.
I guess I'm starting out with this side of the story with photometry, just to show you what we use it for, and it's used to not just do estimates at one point in time, but to do light curves over a long time period. So this is an example on the AAVSO website of a light curve of Betelgeuse, and this was, you remember when it dimmed for a while?
Yeah.
Last year, year before.
It was so, so easily recognizable as being very dimmed.
Yeah. So look here.
Must have gotten down a couple of magnitude brightness.
Right. Exactly. So that's what this shows. So this is the normal baseline right here where I'm pointing with my arrow, and then over here where it is today. But when it dipped down, it went down like 1.5 magnitudes, down to magnitude 2 or so, 1.82,
That
something
was
like
crazy.
that. And you can see that in this light curve. And this is in the, I guess that's showing in green, that's the V-band measurement right here. So I can turn that off. What is a black? I don't know. But these are the different wavelengths of measurement that people did. Also, that's what these different curves are. So I guess in the blue, it came down quite a bit too. That's what this is showing here. I see, yep. So see that flash, that's a blue. So that's pretty interesting. So that's kind of a use for, that's a typical use for photometry measurements over time, is to draw light curves. And that's really the whole purpose of taking measurements of the light, so that you can see things change. You can see variable stars change. You can see eclipsing binaries. Not only applies to stars, but also to other objects like minor planets, like I said before. So let me go back to my other screen. So this is what the filters look like. They're the photometric filters, the 1.5 inches are the most, I don't want to say cheapest, they're the most affordable ones, but you can get 2-inch filters also, these photometric, but they run $200 to $300 depending on where you buy them from.
For a set or for like
for each one.
Wow.
Yeah, so that's why we do have a set at the MSRO of UBV filter, UBV and an R. I don't know if mine's
but
got the
with these
infrared.
5 filters, you can unlock the secrets of the universe. You
That's
know,
right. That's right. You can study the stars, and then the other type of filter we use to help us with that is actually a spectral grading.
There you
That'll
go.
give you a continuous spectrum of a star, not just the bandpass brightness measurement, which is what these do.
And when you amortize that out per light year,
Oh yeah,
used, then it's
pennies.
practically free.
It's practically free. It's less than a penny a light year.
Less than a penny a light year. That's right.
Probably. Depending on the size of your telescope. If you got a small telescope, then you can't really
mileage might vary, but
you can't measure that bright a star or that dim a star with a smaller telescope. So amateur photometry in the 21st century. So before, like I said, the AAVSO, we would do visual comparisons. Okay, so I didn't show that. Let me go back. Maybe I can show a chart real quick on the AAVSO web page. Let's see. So create a finder chart. So a finder chart, if I'm not mistaken, will show us let me see here. And I thought these had the ones for different stars. It should show. I guess this is in a standard chart. The ones that they have, the charts they have numbers next to the different stars. So it'll have it's a visual way of, it says, let's say you're looking at this star right here and you're trying to estimate its brightness because it's a variable. And I probably picked the wrong field because I picked on Betelgeuse. So around that star, you'll have other stars that are similar in brightness, but they'll have numbers next to them. And you can say, okay, look at these stars with your eyeball and say, okay, see how bright they are? Compare that to the one you're targeting and try to estimate what the star brightness is. And so let's say one star is, let's say this one is magnitude 4, okay? This one, and this is the one that you're trying to measure with your eyeball, And then you've got this other one that's slightly less or slightly dimmer than magnitude 4. Let's say it's 4.5 right here. Okay, and you're looking at this one. So now you say, well, that looks like to be a little bit in between these two, maybe, with your eyeball. So I'm going to estimate that at 4.3. Okay, and that's how it works. That's how you would do it.
Now, I recall back during the International Halley Watch, we were trying to measure to estimate what the brightness was of Halley's Comet, the head of
Right.
Halley's Comet. And we were given reference charts. Steve Edberg created this whole thing, and we were given reference charts where he would say, okay, now this star is, magnitude 3, okay?
Mm-hmm.
And what we would do is we would look at the comet, and then we'd switch back to this third magnitude or fourth magnitude or whatever, fifth magnitude star, and we would defocus it so that this light of the defocused image was the same size as the comet.
Oh.
And actually by doing that, we got some fairly good visual estimates.
Oh, that's an interesting way of doing it.
Yeah.
With it now. So you're starting to talk a little bit about an extended object, not just a point source, which a comet
That's
is
true.
kind of. So
that's very true. Sorry
that's
about
real. So no, that's fine. That's a good segue into that. So measuring visual magnitude of an extended object is an area. So a point source is rendered on an image or in your eyeball, actually, also as a point spread function. Okay, all the light is the source is a point source. So basically, it's as focused as you can get. Basically, when you try to do a brightness measurement that way, when you do a comet, like Scott said, to get a more accurate, you want to make the star an extended object, and you do that by defocusing it and spreading it out over more of your cones and rods, I guess, in your eyeball, but also on a CCD chip, it's over more pixels.
Mm-hmm.
So it kind of matches, like you said, it matches the size, so that you're actually doing an extended object measurement for brightness. And that's the way it would be done, Cameron, with a galaxy. That's an interesting way of doing it. So you might try that, Cameron, if you're trying to do it visually. Defocus a star to where it's the same size as the galaxy, and then compare the brightness of that. The way you would do it on a CCD image would be very similar, except for the fact you wouldn't necessarily need to defocus it. You would just take all the pixels, all the data from the galaxy, and combine it into one summation of the value. So that's basically what you do with a star, and I'll show you that here. Let me see. I'm going to get past this. I think it's in my book where I have the drawings that I want to show here. Yeah. So let me get off of this. Oh, I think I had it in the same program. I'm sorry. It's over here. So do you see that, my book?
Yes.
So this is chapter 14. This is the start of how you would do this. First pictures I have talk about the point spread function and what a star looks like on an image. Okay, it's extended. Now, when you do brightness measurements, which are the next thing here with the drawing right here, you basically draw a circle around the star, and you sum up all the each pixel. So each pixel gets translated into a number. It's usually a 16-bit number, which is from 0 to 65,000. And they sum, you do a sum of all the pixels that are in this annulus. You draw this annulus around it. And then you have to subtract the background light from the background. So that's what this annulus is for. So you have two parts. You've got the aperture, which is the center part, where you sum all the light from the star, and then you subtract the background. you would do a very similar thing, or pretty much the same thing with a galaxy. You would draw a circle, or some programs let you draw an ellipse to be able to either surround a trailed star or a galaxy if you can fit it in there. You could sum up all the light from that galaxy in that aperture and get a number, and then you subtract the background like you do with the star, and then you do a relative brightness measurement to another star. So that's how you would do it. Does that
Right.
make sense?
Yeah.
So let me go back here. One of the things that I didn't cover, I'll just talk about for a second. You've got this point spread function on the star when you do an image, and it looks like this when it's spread out on a CCD chip. And the neat thing about this curve is that you can do a calculation on the data that's within this circle and calculate the centroid, which is like the center of gravity for an object, or a center of mass, or it's called the centroid on a flat two-dimensional
Mm-hmm.
calculation. So basically, based on this, the brightness of all these pixels, you can determine where that star's position is within 0.1 pixel. That's the neat thing about it. It's a math.
Oh, yeah.
It's a math thing. So here's what the calculation looks like. Okay. And this is just demonstrates different brightnesses of the pixels, and then it calculates the centroid of the X and the centroid of the 9, and you can see it's very accurate within a pixel, 2.26, or precise, I should say, in 2.319. So from that information, even though you got a blobby star, you can calculate the position very precisely.
Hmm. Very
And
cool.
it's pretty amazing. A simple equation like that lets you do that precise measurement. So that related to last week's talk in terms of astrometry. So we use the same aperture to do the same thing except for brightness. We just basically add up, like I said, add up all the pixels and come up with a brightness number. And then we can relate that to all these other stars, or if it's a galaxy, or if it's an asteroid, if it's anything that creates light that you've measured on your CCD camera, you can measure the brightness. Now remember, magnitude is a relative measurement. So let's say we've got this, we're measuring this object right here that's on the, I can zoom up a little bit on that so you can see it. So let's say this object right here is an asteroid, and we don't know what the brightness is. We can actually compare that to another star like here, or or this one here, and calculate the relative brightness between the two. And then when you have the relative brightness, let's say this one's 0.56 magnitude brighter than this reference star right here. All you have to do then to get the actual magnitude of the asteroid is add the 0.56 to the magnitude here. Let's say it's 3.2. So you add 0.56 to 3.2, you get 3.76 is the magnitude of the asteroid. That's how it's done. That's in simplified terms. And so there's also, I don't know if I'm going to get into that. There's a thing called instrumental magnitude, which is basically a reference. It's basically just calculates the star brightness counts and turns that into an instrument magnitude. It's not in reference to any star. And I'm not going to say any more about that. It gets to be more complicated after
Right.
that. And the book goes into that stuff. You can see here there's a little bit of math there. I don't know if there's anything else. Okay. So this shows you another reference that you can create. Some programs let you create an artificial comparison star, and you can set the number of pixels that you want to set in terms of the brightness, I should say. So it lets you compare your objects that you're on your image to a reference star that you created. There's a program that I've used back. It's called AIP4Win that lets you create these artificial stars to do the comparison. So let me go back to the presentation to see if I've forgotten anything. Oh, one other thing I wanted to show. Where is it? Right here. I think this is it. Oh, that's the AAVSO stuff. Let me get out of that. Let me go back to my presentation. If I can find it. Here it is. I wanted to point out something else. Back to the visual. On star charts, we've talked about star charts in 2 or 3 episodes, but the way magnitude is shown is by the size of the star on the chart. And you've got this reference right here, the legend right here that goes from magnitude -1 all the way to 10, basically, which is this little tiny dot. I'm not sure you can see it. Let me see if I can. You can see here. Oh, thought there was a dot there. There wasn't one. So 9, this only goes up to 9. It doesn't have dots for 10.
They don't have dots for 10.
It's too dim.
Yeah.
Although they do have focus on this triatlas that I'm showing the example of. They do have special charts for specific objects that go down to 10, 11, I think, 11th magnitude. So it's curious that he printed the number 10 on the chart and didn't have a dot for it. But you get an idea here. So you can see Castor and Pollux, how big those stars are. They're really bright. So Scott, pretend this is the sky and you're comparing stars to make a visual estimate. What magnitude do you think Castor is based on that legend?
I think it's like magnitude 3 or 4. 4.
You think it's that? I'm thinking it's between 2 and 3.
You think it's between 2 and 3?
That's the way my eyesight.
Oh, Castor I'm sorry. Yes, the bigger star over there.
Right.
I was looking
you're looking
right
at this
above
one.
that. Yeah.
Okay. No, that's no problem. All right. How about this star Tau right here?
That star right there, probably 5.
Mm-hmm. Very close to 5.
Mm-hmm.
So I think you can see on this chart. So some charts bend the magnitude into whole magnitudes. This chart seems to create the star size, the correct size for the magnitude.
Yeah, because it's between 5 and
right.
4.
So, for example, these 2 stars here, this looks like between 8 and 7,
8.
right? So it's like 7.5.
Yeah.
And this one's like below 9. It actually looks smaller than 9. 8 and 9, the dots look similar in size here.
There is a dot for 10. Look, there's a teeny little tiny dot for 10.
Oh, there is?
9. Yeah. It's like a
Is that it right
salt
there?
grain, like a black salt grain. It's very tiny.
I'd be I guess it is. I'm moving it around. Maybe that's what I saw before. So it is that little tiny thing there, but I don't know if that's true value or not. Well, could be. Well, there's one right there.
Yep.
There's a salt grain. So anything that's 10 and below, they probably just plot with this little dot. All right, so I was wrong about that. There's 2 here.
Mm-hmm.
Let me zoom up a little bit more so people can see. Oh, you start to see them now. Look at that.
You're getting your night vision against that white paper.
Yeah, that's right. That's right. You start to see That's right. So it's 1 pixel or one dot on this.
One
this
dot. Yeah.
Those are all the 10th magnitude stars. You can see
Lots of them.
Bunch of them. Yeah. That's kind of neat. It's just the scale didn't render it because I was zoomed out too much. So
Cameron
that's
says it's a dust spot on my tablet.
that's what I thought it was too on my screen here, because I do have a couple of dust spots. But so that goes back to that. Where am I going? I'm going to go right here.
Martin says this is probably a good tip. If you measure a lot on a chart, you can use a draftsman's template of circles. Use it to compare.
Yeah, you could. Yep,
Mm-hmm.
you could.
Good idea.
So this in my presentation, I talk about this aperture measurement. So it's called the Aperture Photometric Measurement System, where you use an aperture around the star and then an annulus around for the background, and you subtract the two to get the sum, or to get the star only. So remember, when a star shines through or any object shines that's outside the Earth's atmosphere is there and it's glowing all the time. And then when you see a star beyond the atmosphere, the light gets added to that. That's really basically why you need to subtract the background to just measure the star's brightness. Otherwise, it gets artificially inflated. And especially if you're in a big city and you're trying to do a star measurement,
Mm-hmm.
and if the sky is really bright, it would throw you way off if you didn't remember to subtract the background. Let's see. So here's a minor planet that I measured. I can see it right there. It's 2001 L07. And this is an example of the measurement right here on the program. I think this is Astrometrica that I used. And it calculates not only the position of the asteroid, but also the brightness. It uses a calibration. So I pick a star. Basically, the way it works is I pick a star to calibrate this intensity by on that frame that I know the magnitude value, and I put that in. So I clicked the star, measured the intensity, which is basically the sum of all the counts within that annulus, and I tell it what exposure it is, and I tell it what the magnitude of that reference star is. And now when I position the asteroid or the rings over the asteroid, it can tell me here what the magnitude is for that asteroid. But here right now, this is the measurement for the reference star. And so the whole end result of this is to do light curves. Okay, like I showed you with Betelgeuse. This is a light curve I did of minor planet Ringo Starr. This is named after Ringo Starr.
Oh, really? That's
4150. Yep. Mm-hmm.
cool.
And
Cool.
and I used a 24-inch, a 0.61 meter telescope that I had access to back then in 2010. And this is the light curve I measured of that minor planet. It's kind of cool.
Yeah.
So basically, from this light curve on a minor planet, you can calculate the rotation rate of the planet, and it's called the period. And this is a period down here. I don't know if you can see that. I'm going to zoom up a little bit. You can see that on the chart here. Whoops.
Hmm?
So the period
I
of
see
that
it.
minor planet is 6.5 hours, plus or minus 0.3. That's the calculated period, which is kind of cool. You can detect the asteroids spinning out there in space just by looking at the light.
Yeah.
I always thought that was cool.
That is so cool. It is.
And then, of course, at the MSRO, more recently in the last few years, we've been doing transit measurements with exoplanets to do with the light curve measurements with that. So are there any other questions?
Well, there's some comments here, so let's look. It's a good question from Chris Larson. Let's see. Okay. Martin Eastburn, is color taken in effect, or is this a ratio of some non-person color sensitivity?
Right. So it is in reference. There is a pass band that you measure stars in. It's a wavelength. The wavelength filter. That's what the filters are for. And the V-band filter was specifically designed to replicate the visual response of a human eye in most respects. And it's probably not perfect. It's not going to be perfect at all for everybody, you know, for any one person, but it's close. So you can do comparisons between visual measurements and instrument measurements with the V-band filter. So yes, magnitude values are very dependent on the wavelength of the light. Stars emit light in different wavelengths. It's a continuous spectrum. But when you're doing a point measurement or a single measurement like we are with our eyeball, you have to take that into account, and then also you can determine other information from a star by doing different filtered measurements. But again, the spectroscopy, you get a continuous spectrum to do a more precise measurement of the type of star also.
I see. I see. Chris Larson says, I know this is probably not an easy question, but is there a simple explanation for how a beginner can get involved in photometry? Equipment, cost, procedure list. I just joined ALPO and AAVSO for your information.
Okay, great. That's good.
Well,
So
joining those organizations, first off, they're going to get you going. So
that's right. There's a lot of materials available to do stuff, but as a beginner, I would start out with, and he didn't say if he was imaging or not. I assume he might be imaging.
yeah.
So I would start out, and it's for a beginner, can be somewhat expensive. But if you start out with a V-band filter, and he talked about spectroscopy, right? So the filters are like a
Photometry.
The photometry with filters is kind of like a poor man's spectroscopy in some respects, although it costs more money because the individual filters cost as much as a spectral grating. But working with a spectral grating is a little more difficult than just working with a basic filter. So in terms of beginning and learning stuff, it's best to start with a filter and learn about stars and spectral and the difference in magnitude for stars and the different pass bands for the filters. And let me bring up the picture again. If I can. Was it here? Oh, here we go. So this is. I think I had the chart on here. Up there it is. So when you measure a star, okay, depending on what type of star, if it's A type or B type or B or G type, whatever it is, it's going to have different values or brightnesses in each of these pass bands. Okay, each one of these is a pass band. So you can learn about star types and easily with these filters because what you have is the difference in magnitude between each of the filters. So let's say, for example, a star is a red star. It's going to be brighter in this red region than it would be in the blue region. And you'll see that when you take two measurements of that star, one in the blue, one in the red, you'll see the red is brighter than the blue. And that's called the basically RB measurement, or V minus B. It's a V minus B measurement. So if V minus B, the value is positive, then it's a bright white like star. If the blue is much higher than the red. If B minus V is negative, then that means it's a red star. Okay. So that's basically how you would get started looking at light for stars and learning about the spectrum of a star. Now, and then you can move into a spectral grading as another. That's the next that's the next thing you would do after you've mastered looking at stars through the filters. If you want to learn about the star types, then you would move to a spectral grading in a filter wheel, and then measure the spectrum. And then you start matching the spectrum. You have to correct the instrument. You have to do a lot of calibration to get an accurate measurement, which is why the filters are easier to use, because they're already calibrated and you don't have to do a lot of math to figure out what type of star it is. But once you get into spectroscopy, you'll have to start getting into all that stuff, calibrating your measurements with the spectral grading. And then from that, you can compare the light curve, or I should say the spectrum of the star, to what you measured, and determine what type it is, what type of star it is, and then start looking at features in the spectrum itself. So that was a kind of a long-winded explanation of how to get started in spectroscopy, but it's similar to getting started with telescopes. You might want to start with a pair of binoculars before you go to a telescope.
Yeah.
It's the
And you
same
could
kind of
use that
thing.
defocus method. I think you could probably even do it on other stars, because if
Oh
you
yeah,
focused, let's say it's a third magnitude star, you think that you're looking at another third magnitude star, you could defocus the reference star to a certain size and defocus the other one, and then compare back and forth,
right,
and see if
right.
it looks fainter or brighter.
You
So
know,
I
it'd be
think you
kind
can
of
make little
interesting to do.
subtle.
Yeah,
That,
you could almost. It'd be interesting to do that, in terms of, and correlate it with a focus position, in terms of the difference in the brightness. That'd be kind of an interesting experiment.
So any other, let's see, Jerry, I'm looking forward to calibrating my imaging system. So we could use imaging software to reliably and constantly measure magnitudes of stars and galaxies and comets and DSOs. That's from Cameron. Let's
Yeah.
see.
The thing is to learn the basic techniques and
Yeah.
the engineering behind the measurement, right? In terms of, I don't know if engineering is the right term, but the details of the measurement. Okay, and then you can start saying, oh, I can apply it to this, that, and the other, and this is how I need to adjust my thinking on it. And you can
Mm-hmm.
come up with your own techniques on special objects. If you have something that doesn't quite, it's not a star, it's not a galaxy, it's something else maybe that you want to measure the brightness of. You can adapt these techniques, like Scott said, defocus method, doing some things, and then also, but in terms of measuring brightness level, it's all comes down to summing up the pixels on a CCD chip,
Mm.
and that's the value. That's the correct. That's basically what it is. It's a linear detector. It's a linear light detector that is an instrument to measure the brightness of things, and you just apply it that way.
Let's see. Jenny Bedell Shelley says PhD 2 locks onto a star centroid.
Mm-hmm.
Um,
Yeah, these techniques are used for a lot of different purposes, and in terms of the measurement of the
mhm.
brightness. And like I showed you, astrometry, the centroid calculation, that's really cool that you can do math on the pixels, calculate the centroid, and then you can do math on the pixels to determine the brightness, the magnitude of the object. You can do. I'm sure there's other things you can do with that, with the image of the star. Also, some other calculations that people do.
And Martin Eastburn says, I would think they would be more like the IC curve, where the V is our optical curve. The others should be bandpass of high grade.
Yeah, so since those are other wavelengths that we don't see with our eyeballs, they could come up with the way they wanted to do that standard. It's basically whatever standard. There's other standards like the Sloan standard for measurements. It's another photometric system. It's called a photometric system when you have certain standards for the different wavelengths. Um, yeah, there are multiple other standards. If you look at the Hubble Space Telescope and the filters they use another completely different standard that has a lot more filters in it, but it's got a much wider range of measurement also in terms of
Mm.
wavelength.
And Jenny wants to know, would broadband RGB filters be a dirt poor man's version of photometric filters if
Yes.
imaging with a mono camera?
Yeah, you could. So one thing you can do, which is kind of interesting, is if you just have a regular, and I did this with just a regular green filter. I correlated a green filter response to the V-band filter. And what you
Okay.
do is you just, like I use M67 as a good reference for magnitudes for different stars that are different magnitudes, and I plotted the catalog value for each of the stars and on one axis, and then plotted my measured values on the other axis, and then you draw a line through it, and then you get a relationship between your green filter and the visual magnitude. That's the reference value. So then all you do is you take your measurement, and then you can take a measurement of any star and say, okay, I measure this with your green filter, and then you say, okay, I measured this magnitude. I correct that with this calibration curve that you created, and you correct it, and you say, okay, that's actually V-band this, or other, and then you can do that with any of the filters. So with the regular RGB filters, that would be a poor man's um, spectroscopy for star type measurements. But you need to calibrate it. You need to have a reference filter measurement to compare it to also, which there are references out there. So if you have a red filter that you want to calibrate, that's just an R filter, and you can look up in the catalog, okay, what's the R magnitudes for all these stars in M67?
Hmm.
And that's what you use as your reference.
I see.
And so you take the measurements yourself with your R filter, with your red filter, and then you compare it to the catalog value, and then you create a curve. It should be linear, should be a linear response. So you just do a least squares fit when you plot the catalog values on the x-axis and the measured values on the y-axis, and that's all you do. It's just math. I know a lot of people
Just
shy
simple
away from
math,
math.
folks.
Simple math, that's right. It's the least squares fit. So there's a lot of magic you can do with math that makes up for a lot of things, that you can do with equipment that we have in hand. That's another side of amateur astronomy.
That's true. Martin Eastburn says, I suspect it was the chemical mask they figured out and used. In machine work, we have 10 filters across the band.
I'm curious, what exactly?
Not sure.
Oh, I'm full of something. No, I try to be as my tendency is to be more complete than necessary, to try to I talk more than what I probably need to on a lot of things, but I try to be accurate also.
Yeah,
AIP for win. Yep, that's a good
there we
program.
go.
I don't know if it's so.
I don't know if Martin wants to elaborate a little bit more on that.
Yeah.
Maybe he was talking to someone else and I'm talking out of turn. So, anyways, well, learning photometry is a great stepping stone towards getting into the science, becoming a citizen scientist. And
Right. That's the next step after astrometry. Astrometry is good just to exercise your skills on doing calculations and figuring out things. Photometry is where you really start to do some science and do some measurements that are applicable to different questions about the star types
right.
and things like that.
Now, something I want to kind of talk about a little bit is the American Astronomical Society. They have, I guess, for a few years now, have had an amateur level where you could go and become members. Jerry and I are members of the American Astronomical Society, and I have been involved a little bit in their advisory board for interesting more people that are amateur astronomers into the AAS. Now, the AAS, I mean, that whole scenario is about preparing amateur astronomers to become, really productive amateur scientists. And
Hmm.
so you do need to learn your ropes a little bit. And, working with Jerry and the MSRO is a great stepping stone towards really refining some of those skills so that that you can join a group like the American Astronomical Society, and it costs, I don't know, like $50 a year or something, and you can get involved in these pro-am projects. Okay, and when you're on a pro-am project, a lot of times your name appears in the science
Oh yeah.
documents.
If
Okay,
you
so you
provided
become
observations, yes. If you
published with these
hmm.
guys. Okay, and so and for I mean, that's a thrill all by itself. And um, so but one of the when I was sitting in on some of the lectures, one of the things that was kind of, they sort of lament, some of the professionals, is that they have amateur astronomers that want to give them data, but the way that they've collected is it's too sloppy a lot of times for it to become good data.
Right.
In
Right.
those cases, what they'll like for Halley's Comet, they were not sure that they could get a lot of really accurate data from a few people, so they spread it out to hundreds or thousands of people, and then they averaged that data, what
Yes.
they could collect, and there they could get something that was a lot more accurate.
Right. So
But
it's right.
but
So
it always
statistics is a
counts,
big thing. Yeah. Statistical measurements. That's something you'll run into also when you start getting into this as statistics a
right?
little bit.
But if you learn how to do some of this, and you start attending some science symposiums and stuff like that, you get to a point where you can retire, or you get a little bit more free time that you might have not have otherwise have had. But at this point, you may become a candidate to actually work in an observatory. And that has opened up for a lot of amateur astronomers throughout the years. And so I think that's great. One of the people that is on our global star parties, Rodrigo Zaleta, who owns
Hmm.
North Optics in La Serena, Chile. He's getting his degree to become a research astronomer, and he hopes to be doing professional astronomy as well. So, but it could happen to you, and this is where you start. So,
Yep. Yep. Learn the
okay,
all astronomers that work to do measurements learn these basic techniques: astrometry, photometry, and spectroscopy. And it's no different between the amateur and the professional. I don't, and I, as Scott knows, I've talked several times over the years about we're all astronomers. It's whether
yes,
we get paid or not to do it. That's the only difference, and we love it. That's what amateur means: is they love it for itself. They don't want to get paid. But again, I just like to refer to all of us as just astronomers.
right. So let me see if I can give you guys a link to the American Astronomical Society membership page.
Yeah, they've got a wealth of information, and you'll start once you get involved with the AAS, you'll get contacts with professionals and be able to talk about what their work they do and what you're interested in, and they'll be able to steer you. I think you'll be able to make contacts with people that will help
Yeah,
you give advice on where to go for different things and who to contact in the professional side if you're interested in the work that they're doing.
they call it the amateur affiliate program.
Yes.
But it's $53. It's very inexpensive, especially when you consider what it costs for a pro to join the
Oh yeah.
AAS.
Right.
It's much more expensive.
And you get access to you get the newsletters and you join
Yeah, you
different
get a
groups.
you get a discount to Sky and Telescope
Yeah.
magazine, um,
Well, see, that's the
and
other thing. They're really reaching out to amateurs because they purchased Sky and Telescope.
that's right.
Yeah.
That's right. And they see amateurs as an important resource for gathering more data, but there needs to be kind of a concerted effort to doing the training, and so groups like MSRO, the AAVSO, ALPO, some of these groups are and there's probably more around the
Oh yeah,
world
yeah,
that you could be getting involved with. You can start to do some of the science that's out there. It doesn't mean you have to give up, loving the night sky or making beautiful images or all, that stuff, but
right.
this just adds to it. So,
Yeah, so that's right. Astrophotography, there's two sides to the astrophotography. One is to do beautiful imaging, which is great. That's what gets
it's
people
very
interested.
inspiring,
Well,
right?
that's what gets people interested in astronomy in the first place, is see these inspiring images, right? So
Yeah,
that's important. That's a very important piece. But once you get into it, you may be wanting for other things to do also, which is where the science side comes in. And there is some stuff extra more to learn. There's nothing wrong with learning more stuff about your hobby.
that's right.
Uh, don't be
Well, you
scared
got to
to.
keep those juices flowing in your
That's right.
brain,
That's right.
so,
Don't be scared of learning something new or picking up
oh,
a little bit
that's
of
right.
math.
If you don't know the math, learn how to,
Right.
you can take, you can get all the way back to total beginner's level, which is what I would have to do for a lot of it. But, I think it's fascinating and it adds a great dimension to your hobby and your enjoyment of astronomy. So,
Right.
all right. Well, that's great. Well, tonight we've got the 54th Global Star Party. The theme of it is the impact of comets. And when I talked to David Levy about this, he got well, you can imagine, he got super excited. So he is going to conduct a discussion panel, which is a little bit different than the format that we normally have for Global Star Party, but discussion panel on comets and, the way that comets have impacted our lives, throughout humanity. Certainly comets were, I mean, they scared, people around the world, when they would see something up there like that, I guess it was King Harold that on the Bayeux Tapestry in the, I think it was 1066, it was recorded about the conquest of England by the Normans, so he certainly saw it as bad luck, and then comes around Edmund Halley, Isaac Newton, and it's really surprising how much insight Isaac Newton had into comets, because he described comets as being kind of more or less a solid body, and he suspected that the sun either heated up the comet or that it ignited the comet, okay? And these vapors would come out. But he believed that water on Earth came from comets. He believed that the elements of air that we breathe came from comets. So these guys weren't far off. And they really, they were,
Yeah, they
Edmund
had a lot
Halley
more
was
insight.
able to figure out the orbital period of Halley's comet, but these guys are really working in kind of the dark ages of
Yeah, they had
science.
certain. I mean, the Greeks had very accurate, in some places, accurate type of philosophy and outlook on and how things were made. Right, the atom.
Yeah,
Basically, they believed in the atom,
yeah.
and
So there must have been like this basic um, way of looking at the world that led them to have very accurate predictions of how things worked.
mm-hmm,
So.
mm-hmm.
So this is pretty interesting. I need to read up more about Isaac Newton and his, his observations of comets. Because so much of it is attributed to Edmund Halley. And Halley and Newton were friends. So
Mm-hmm.
in fact, a lot of people say that almost no one would know about Isaac Newton had it not been for Edmund Halley.
Oh, really?
Because
That's interesting.
yeah, because Isaac Newton was not like a really friendly sort, and so probably if you weren't at or near his level, he probably didn't have a lot of time for you. Okay,
I see.
is what I suspect. And you know, I think I've heard that he had a temper, and you know, so you know, and while you know Edmund Halley was kind of a popularizer in some ways, but also, you know, a very smart guy and a scientist. So, you know, we have there's that whole story. But and a lot of us can point back to the inspiration, what inspired us to become amateur astronomers in the first place. My story is, you know, it actually goes way back to when I was a little boy, but I can tell you that when Halley's Comet came around, that's when I started getting very serious about amateur astronomy. And so, you know, I love to look at comets, and you know, and so I'm a wee bit disappointed that this really giant comet that they have been talking about that's coming is going to be too far away for us to see anything really spectacular from it. But you never know when another really amazing bright comet might come. So we hope you watch tonight. It will start at 8 Central, 0100 UTC, and should be a really great global star party. Hope you participate. Anything else you wanted to add, Jerry?
No, I think this is the next program. I'll be talking about spectroscopy, I believe. I think that's when I'll start digging into spectroscopy, and I'm trying to keep these at a fairly high level. There's always more and more detail you can talk about. So
sure.
And I do have a tendency to ramble on into the details a little bit. So if anybody has any other suggestions, if I'm keeping the level good for everybody, that's great. If I'm going too deep, let me know, you know, that type of thing.
Well, that's what the questions are for. That's why we have chat here. Okay. Again, thanks to everybody in the audience for the great questions and comments that you had. We're all learning together, so that's really cool. And we'll see you tonight. So take care. Here's the Explore Scientific iAXOS 100 Equatorial Tracker mount. We've got it mounted up here with a digital SLR that's got the dovetail plate here. We also have it kind of mounted on our extra heavy duty tripod. But this whole thing is operated remotely. You can see Kent's operating it with his Apple tablet here, but it'll run off a Windows tablet or an Android tablet. What do you like about this whole system, Kent?
I find it very intuitive. It's very quiet. Like any go-to system, there are things to learn.
Sure.
But once you learn those things, it makes it really easy to find stuff in the sky.
Sure.
Now, this is running our Explore Stars app. If you're going to do astrophotography, you need to be running it with a planetarium program hardwired to a computer.
That's right. So this runs wireless, wired, okay? It's super versatile. It not only has go-to capabilities, but you can also add a guide scope with an auto guider CCD type of camera onto it. So, and you know, the thing that you're going to really love about this is the price of this instrument, which will fit neatly into your budget, I'm sure. So, check it out. Look online. Check out the specs. Give us a call if you have any questions.